Actually, it's sort of interesting. There are really two Dans, Dan Senior and Dan Junior, and it took me a little while to sort of get this. But so Dan Senior is a bioengineering professor at McGill and has been, really focused on a lot of different bioengineering areas, but this one that he works on with his son, which is the computation using, cells, is something that is pretty novel and pretty unique. Their family story is quite interesting. They came out of Romania. They've been all over the world in various ways. His son has taken the trip from Nome, Alaska to Tierra del Fuego in a car, and we had a nice talk about it last night. But just as interesting people with interesting ideas, it would be worth listening to the talk. But to me, this is, the computation might be limited by being purely digital. And the algorithms, we know that quantum mechanics can give us algorithmic approaches that perform better than our classic serial digital things. But what's interesting is that maybe biology can also extend our range. And with that, let's hear from Dan. So Dan Nicolau and Dan Nicolau Jr.
Thank you for the introductions. And we will try to entertain you today with three things: computation, simulation, and algorithms, all biological or bio-related. Now, okay, I am from McGill now, but there are so many people that could be equally authors to this, so we'll see them in a minute. So I think that it is proper to acknowledge huge number of people that work on the left on this in many capacities, and one that needs to be really, he was from the beginning, the engineer here. And biological agents are on the left, if you like, and the networks are on the right. So someone told me that vision without money is hallucination. Okay. The next thing is what's next. So this is a sort of trick question. I will ask you to give some answers at the very end, if we do have time. Ooh. That's a poll question. How many of you think that you are intelligent here? That was one answer, I guess. All right. That's it? Don't be shy. Well, it is clear that nobody thinks that, well, 6%. All right, let's go on. That can continue on and on and on. And perhaps we would like to hear what is that you think at the end. The other thing is that we'll talk about biological agents and networks and computation and simulation, but the red thread here is, if you like, intelligence. So that was the trick question. And we will come to that a couple of times. So what you see there is, you see two things, actually. You see agents. They are moving around, possibly aimlessly. They do not interact with each other. And the other thing that you see there is a network. And as a matter of fact, there are two types of networks. One is that the one in the middle, the large lines. So there is a structure in the network, and there are others on the sides that are kind of blurry, and they are not structured at all. Okay? So in the first instance, if there is logic in the network and the agents are exploring that network, perhaps that can go to computation. We will come to that later on. However, if the agents explore a network that is not structured, so we did not build that network, perhaps they are doing some other actions other than proper computation. There are no numbers there. Okay, so that is just setting the background. By the way, The green worms, they're not green, by the way, but we color them for your pleasure. They are actin filaments moving on surfaces that are black, that are functionalized with molecular motors. They are pushing the filaments. Okay, but we'll come to more technical details later on. Sorry, not again. Okay, so we finished the introduction to the introduction. Now let's go to the introduction proper. So we'll talk a bit about unconventional computing, the motile agents, then we'll biocomputation proper, biosimulation, biological armories if we have time, and the sum up, and perhaps a word about innovation. So everything here is about innovation, but we didn't look that actually in the process of innovation. Okay, setting the background. So unconventional computational, in our case, biocomputation, perhaps computing, so quantum computing is also unconventional. So we are thinking that we can use biological entities, for instance, DNA, cells, whatever, cytoskeletal filaments in our case, for solving non-trivial mathematical problems. Okay, if they are trivial, perhaps we shouldn't bother. The other thing is that is when we think that we are intelligent. So this is what it is coming to that question that I put a few minutes ago. So this is at the one end of the spectrum. We are the intelligent guys. We build networks, and we'll figure out later on. However, we may kind of lose that thing, and then if we do not calculate proper, okay, we can do simulation that is not passing through numbers. We do not make abstract formulation of the problems, but we just want to see how it goes. And I think we will touch in a few slides this idea. The other thing is that if they are intelligent now, and we are sort of, I wouldn't say that we are dumb, but we take lessons here, we can drill into biological algorithms. Okay, so if we will have time, we'll see a little bit about that. Now, if we are talking about natural computing, actually this is, I'm plagiarizing this. This is an image from one of the many theses that Dan Jr. had. So we are talking about natural computing. In our case, most of it is biocomputation. We can be at the hardware, okay, or at the software end. So that kind of maps what we just presented one slide before. Now, computation with networks. Most mathematical problems fall in two categories. There are the simple ones and the very difficult ones, NP-complete problems. They are intractable for a decent size of the problem. Okay, so examples of those would be, the most known one is TSP, travel salesman problem. But there are other problems that we love, knapsack problem. We'll talk about it in a second. The applications are multiple. Cryptography is perhaps the one that comes immediately, but many scheduling problems and strategizing and so on and so forth. So what did strike us is that the difficulty is not about operations. We are not talking about differential equations or something like that. The operations are very simple. The problem is that they're enormous. I cannot say huge anymore these days. Sorry. Huge. All right. And not only there are many, but they are growing on and on and on. Okay. So, but once that you have the solution, you can figure out very quickly if it is true or not. You can verify it very quickly. So then we thought, actually both of us, we thought, what if we do this? What you see there on the right. So is that okay? So I heard that is the black. So what if we do this? We have a mathematical problem. We encode the mathematical problem in a graph. From there, we can fabricate. We first design and then we fabricate that graph in a network. And then we have a pool of agents, biological, hopefully, but can be others, and let them explore the network that we just conceived. And here we get the pool of solutions. Now, in the network, the network can be passive, but perhaps mostly in the future we can have gates that are changing in time, or they are controlled, and so on and so forth. Okay, so that's the basic concept of the power of computation that we proposed. And,
excuse me, on your left, sure. Can I ask you a quick question? Let me state it simply like this. We're the only species that try and optimize anything. All biology is good enough. It gets close enough. And in all my work on things like the traveling salesman problem, using these kinds of techniques, we've always finished up with a really good enough solution. So could you just emphasize for me what you're hoping, or what you've actually achieved here at the end point? Have you got a really good approximation to the truth, or are you claiming precision?
We are claiming that we have the whole lot.
You're getting, with biological and analogies or entities, you're getting absolute precision.
Yes, we get all the answers that we need. Would you?
Perhaps I can take this. So you can use heuristics to find approximations to the problems, to the instance of a problem. What we're claiming, and what you'll see in a few slides, is that using lots of agents, you can find the exact solution. So as you know, there are some instances that are more amenable to approximation than others. So what we're doing here is calculating all of the possible solutions, exploring the entire space, and from that emerges the precise solution. Okay, so that I fully understand this, what you're saying is in the bag of solution options you get, somewhere in there is the optimum. Correct. And so the $64,000 question is, how do you know which one is the... Oh, you'll see in a minute.
We'll come to that.
Okay.
Could I ask, I'm trying to understand this, but the NP-complete problems, any individual problem is solvable, but the problem is the scaling.
Yeah.
You know,
We'll come to that soon. Okay, so now about the agents. There can be many agents. We focused on those protein molecular motors a little bit heuristically, but they do have certain benefits. One is that they are absolutely essential for life. So molecular motors are really everywhere. Cell division, force generation in the muscle, name it, everything. Actually, there is that image there states about 8 critical biological processes, and I think there are more now. And actually, we are doing a little bit differently. So this is what the movie there is, what is happening. It is an animation, but what is happening in life. But we're doing the other way around, so that we mobilize the motors with the legs upside down, and they are pushing the actin filaments or microtubules. All right. So they are very small. That's very, very nice, because we can pack a lot of operations in a small area or volume. And give or take, they are quite quick. All right. So a few examples. I love the first one, but this is not what we are doing. I love the first one because I have it every year. So yeah, so you have a number of students, and you have far more students. You have a number of places, and you have to place the students in dormitories, and well, the dean or whoever the provost is telling you that they have to be first. There are rules. They have to be the best. They have to be also a little bit, well, classified according to income. You cannot put ladies and gentlemen in the same room, and so on and so forth. So to generate only that, it takes more than the atoms of the universe to generate all possibilities. No way that we have the time or the inclination to do that. The knapsack problem is a nice one. Suppose that you are a thief, no pun intended. So suppose that you are a thief. You are in a room, and you see objects, and let's propose that the objects have volumes or weights with the prime numbers, okay? So you have a sack that is 15 kilos, or we can work it in volume, and you really want to put exactly the same, the objects that fit exactly in 15 kilos or whatever it was. Okay? So you have to permutate all the possibilities, and well, actually you are trying to get out very quickly. So this is another NP complete problem. Okay, so this has an audio.
Traveling through a network of channels. Agents enter at the top left corner. They move through the network and leave through exits at the bottom. Each exit corresponds to a number. The path agents take through the network is governed by two different types of junctions. The first junction for each number in the set is always a split junction. Split junctions are designed such that agents have a 50% chance of turning left or right. Turning right means leaving a number out of the subset sum. Turning left means adding a number to the subset sum. The value of the number added is determined by the number of path junctions following the respective split junction. Path junctions are designed such that agents can turn neither left nor right. The exit at which the agents arrive corresponds to the total sum of all numbers added to the subset. In the path of the example agent, the number 1 was left out at the first split junction, and the number 3 was added at the second. Thus, the total sum for this subset is 3. Other possible paths to this network would combine the numbers 0 and 0 to 0, 1 and 0 to 1, and finally 1 and 3 to 4. No agents will come out of exit number 2. Thus, agents exploring this network successfully find all possible subset sums and solve the subset sum problem in the computation device.
Okay, so that was the principle. Certainly that is just a proof of principle, actually, not yet a proof of concept. But a couple of other details, technical details.
But a question on your right.
On your right. Oh.
So isn't it the case, though, that as Bob Lucky was saying, the number of organisms, as it were, that you'll need to solve this is going to go up exponentially as the number of nodes increases?
Correct. Yeah. So for an exponential problem, we need an exponential number of agents. That goes without saying. Yes, sure.
Yeah, two questions. One is, how does the energy efficiency of this compare with the computer?
We have a slide for this.
Okay, and how fast is it?
How fast is difficult to answer in one sentence. Basically, it depends on the agents, right? So the agents form the hardware on one half of the hardware, and the other half of the hardware is the network. So if you have a network of size x and agents moving at a velocity v, basically the n upon v gives you some idea of how long it takes to traverse the network.
But we have a slide for that too.
Okay, and error correction, do you need that?
And again, there are two answers, two complementary answers. On the one hand, if you have enough agents, they have redundancy. So you have some idea that if nothing comes out of exit number 2 and lots of things come out of exit number 3, the sum corresponding to 3 is clearly possible and correct, and the one corresponding to 2 is not. And beyond that, yes, there is error correction in the junction, so you have some idea of, and the error rates are not 0, they're not identically 0. Hopefully they're close enough to 0 that you can get very good statistics, but it's essentially a statistical game. You're trying to get an idea of whether what you're seeing is real or not.
Well, the reason I ask is in quantum computing, you have an error corrector with a quantum computer attached. Yeah. All the resources are in the error correction. And I'm wondering if that's true of you too, and that kind of takes away from your advantage.
Well, essentially, if you use enough agents, you can overwhelm that. Then it becomes an engineering question about, can you generate enough agents? So in the case of actin filaments, you'll see a film in a minute. But in the case of actin filaments, and they power your muscle, the question is, can you make them small enough that you can make enough of them that you can get them in the network and get readout? So on some level, it's just a question of getting enough agents. And then the underlying practical question is, can you get practically enough agents? For the same reason that DNA computing has this too, can they get enough DNA filaments in order to overwhelm the exponentiality of the problem? But I think it'll become clear with a couple of films.
There is also a biological answer to this. So the two systems that we are using so far, one is actin filaments with myosin. That is very quick. The force is there. However, because it is, you cannot have three things in life in the same time: precision, force, and speed. Okay, so you have to decide what do you have. So with actin filaments, you have the speed, but not the precision. With microtubules, that's a totally different system. Well, it kind of looks the same, but it is very precise. So the errors are not that large, provided that you work on it. I mean, the channels are narrow enough, and you figure out the logic in the gates. So there are benefits one way or the other. Yeah, sure.
Yeah, so by the way, the reason you're getting all these questions, I think, is because what you're talking about is so freaking amazing. But when we're doing this computationally on computers, we typically will start the search from both directions to see if they meet in the middle, because that halves the exponent. Do you have something where you start organisms from both sides and see, so to speak, where they meet or whether they meet?
I'm sorry, I can't see where you are. Oh, there you are. Very good question. So again, I think it'll become a little bit clearer once a few movies pop up, but what we can do is put the agents into the network from different entrances. So you can, left and right is a simple example, so if they need to do a sum, you can put them in starting at 0 and then starting at the maximum number, and then they subtract going to the left and add going to the right. More generally though, if you're trying to do something like a traveling salesman, you can put them into the network starting at any node. Right, and then you just have to have a way to kind of flag them so you know which guy or which gal went into which node initially. But at a large scale, you can put them in principle anywhere, because their trajectories are what encodes the solutions, and in most cases, it generally doesn't matter where they went in as long as you can track them. Does that make sense?
Okay, so more on the technical side, there are two types of junctions. The error is not the same, so in the pass junction, you really have to have the lowest possible errors. The split junction, you can work out. You need a little bit more agents, but errors are not that difficult. Essentially, we are talking about microfluidic channels with molecular motors at the bottom, and whatever cytoskeleton we use, they are actually the biological agents.
It sounds like we get quite a lot out of seeing a couple of the additional videos. Maybe this is one of them.
Yeah, so this is the real thing. So this is in real time. Obviously, there are agents like this one that landed there well, out of the blue. We do not have, there are many technological improvements that we can have here, and we're working on them. So this has no roof. So the agents are coming from the top, but mostly they are, this is here, it is a large pool of agents, as I suggested before, and they are getting into the network, and they are getting, give or take, through the right exits, the right ones, okay? And this is with the microtubules. We have a similar one with actin filaments. Now the scaling, so someone, I think you have been interested in the scaling here. So this is what we calculated. We are kind of here at the moment, and this is how long it takes to solve the knapsack problem, or more properly a subset subproblem, by the best possible Apple Mac, okay? And everything goes fine, even a laptop beats everyone, but around 20-something, the first number of primes, it begins to, well, to give up. So this is the line for actin filaments, which are, as I mentioned, they are very quick, and this is the line for microtubules. So give or take about 30, well, we will beat the best possible laptop. So you move a little bit further, that will be a desktop and perhaps a supercomputer. So our aim is to be here in, I don't know, 1, 2, 3 years. Energy, someone was interested in energy. So we are here, okay? So we are talking 10 to minus 14, as opposed to the really God's own thermodynamic limit, 10 to minus 22. The DNA is beating us, again, because it is very close to thermodynamic limit. But give or take, we are not that bad. Okay, so next thing, eyes on the clock. Biosimulation. So that would be quick. It is more an introduction. But what I want to put some semantics here. If we do have a problem, nowadays we are taking the problem, we formulate the problem in abstract terms. We pump the numbers in a computer, we get the numbers out, we are getting the solution, we like it or not, we implement the solution. Or we are getting a little bit more and more if we do not like the solution. Old days, well, I am thinking of the pyramids. The Egyptians built the first pyramid and collapsed. Okay, they had nothing, they had no knowledge of serious mathematics. They didn't know the number pi at the time, I think. So the next pyramid, well, they figured out that it will collapse, so they finished it very quickly. The third was okay. Okay, so that was what they did, actually. They take the problem, I want to build a pyramid, they put that to test, physical test. They like the solution, not. Okay, so they did a couple of times, but the point is that they did not pass through the abstract. Okay, so sometimes maybe this is better. And one possibility is what our friend Toshi Nakagaki in Hokkaido, he used the slime mold to simulate, to physically simulate the network, a network. And by the way, this is a small network that mimics the train network in around Tokyo. This is Tokyo. Okay. And before that, actually, he played with the same slime mold in a maze. Well, that is different. So there are some algorithms here that, so you can stare at that and say, ah, yeah, that's actually the slime mold found the minimum path here. Okay, but what is the algorithm that the slime mold is using for that? And I think now is the time for the next poll question. So can we have some answers now? So we know there are, I would want to see how many people thought, so you are wondering, but this is one answer, I'm sure. Now, I'm wondering how many people think that they're intelligent, and then when the question comes, do you know what that is? Well, there would be a disjunction there. Okay.
Excuse me, you may get to this later, on your right?
Yeah.
But are you going to ask the question, when you finish this with this machine, will it be alive?
What is it to be alive? What does it mean?
That's what I'm asking. Are you going to ask that? Or if you're not, what's the answer?
Well, I do not know what being alive is, by the way.
Well, no, but it's negentropic. You know, a ball that rolls downhill is dead, one that rolls uphill is alive, and yours is rolling uphill.
I think you'll find this to be a theme in our answers, but basically depends on the agents. So Dan's not talking too much about it, but if you use bacteria in these networks, which is sort of an obvious thing to do because they go like 500 body lengths a second, self-replicate, eat anything in their path, clearly it's alive. Most of us would look at these guys running around in a, you'll see in a minute, a network that is a city, a copy of Venice. That's clearly alive. In the case of muscle proteins wandering around on the surface, they're self-propelled, but the answer is a little bit murkier. I'm not sure if I would say it's like a virus, it's partially alive, whatever that means. And in other cases, most of us would agree that it's not alive. So it kind of depends on how alive the agent, because the agent's the hardware. It kind of depends how alive the agent is, if that makes sense. Okay,
running eyes on the clock. Biological agents, a problem that we love is space searching. Okay, space is a premium, not that much in Canada, certainly not in Australia, but in general it is a problem. So we like to use fungi. They are incredibly good in finding all places, or narrow entries and so on. And by the way, as I promised, they use heavily molecular motors. These are the microtubules, and the molecular motors are carrying the vesicles on molecular motors. Okay, with that, what we tested long ago, actually, we presented the fungus to a set of mazes. And this is addictive. If you look at the students are really trying to do that again and again and again. But if you are staring at that long enough, you realize that the fungus has a biological algorithm. And we tested now about 6 species, and all of them have, not algorithm, they have a program, okay, a master program with 2 subroutines. The first is collision-induced branching, meaning that they will grow, but when they cannot, they will send a branch, but not before. It is like us. We will do the same thing, but if we cannot do it anymore, we'll try to find the solutions. The other one, which is freaky, I have to say, is directional memory. Each branch will go into the direction, say, it was born heading north, it will head north, it has to turn left, right, whatever. The moment that it has the opportunity, it will go north. So it is like having a compass, like us again. So we'll go all places, but eventually we'll get home. So when compared with other algorithms, so here we have the comparison with 2 types of algorithms. One is depth DFS, which is an uninformed algorithm. So the fungal biological algorithm is beating that one. Of course, if we are comparing with something that is an informed algorithm, like A star, it is not going that well. But give or take, just the rough biological algorithm is good enough to be compared with others. And this is without trying any optimization, without trying to comprehensively look for what algorithms are using, the fungi are using here. I guess that we are close to sum up perspectives. And perhaps a word about innovation. I think we have time also for questions. So when it comes to computation with networks and biological agents, we did solve a small instance of an NP-complete problem. Just demonstrated how it goes. Certainly there is a lot of work to be done there. Logic of the gates, different designs of the networks, different agents, tracking the agents, and stamping the agents, IDing the agent, and so on and so forth, and interfacing with the real world. In biosimulations, that's very nice, but the challenge there is that we need to work ahead and go beyond the metaphor. Oh, this is traffic of the fungi or whatever, and it looks like the traffic in real life. So we need to go beyond that and use that. Okay. When it comes to biological algorithms, I really love that one, because what I think, for instance, mimetics, we are very advanced in materials, okay, biomimetic materials, but not that much in biomimetic IT. What I'm proposing is that we can go in harvest biological algorithms. As we do harvest information, we are going into Amazon forest and to figure out new DNA for new drugs or whatever it is. But there is a lot of work to be done there. This is not the last slide, but I love this quote. And I think this is actually the problem that we have. Now, a word about innovation. I cannot speak in general, but I can tell you the story, our story of innovation. So I think that how is that happening? First, you have to have a big perspective, okay? And then you have to look at the fundamentals there, okay? The other thing that you need to do in order to have, very new ideas is to ignore the warnings, especially if they are old, okay? But the other thing is that you need perhaps more people, because there are things that you cannot see, but others can. And this is, I think, what the engineer saw, and this is, I think, the moment when he figured out that we can do something with many biological agents that were hanging on my back. Well, actually, this is very like academic life. The other thing, you have to work hard, each at his own pace, okay? And eventually, we had the other side of the story, and that's the networks. So this is us at Grand Canyon, Actually, I do not know what was your problem there, but I had a toothache, terrible toothache, and I self-medicated myself from San Francisco from all pharmacies. I took all of it, and that was the result. So the MP guys are here. And what's next? What do you think it is next?
How about optimizing the organisms? Because,
That's next.
Well, I was talking about your problem. In all the computer simulations of biological organisms to solve these class of problems, the next step is to actually breed better organisms, and you can tune them. And it's, as far as I understand it, it's actually in the real biological world, that's a little tougher, but it's not impossible to do.
I was serious. The answer to this question is this. but there is, and with that now it is the time for questions. Yes. So we used, for fungi, for instance, we knew that molecular motors are somewhere there, and we played with the mutant. The mutant, the poor mutant cannot live in real life because it's defective in molecular motors. But the thing is that, you're right, in life, the fungi are branching at 45 degrees. Why? To generate a fractal cover of the space. Now, this mutant cannot. It is so defective that it sends branches at 90 degrees. And this is okay for us. So that solves better the maze because our mazes were orthogonal. So yes, you're right. We can play with the genes to fabricate the agents that will solve the problem according to our networks.
I'd like to just connect with you on one thing, and a pint of beer bet on this. I'm going to bet you that the optimum number of parents in the biological world will turn out to be 4. You will need 4. You will need 4 species to get the optimum biological solution. If you get that, if you do that, let me know.
I'm going to ask you to stand by just a moment. So there's always a back channel in these presentations. To me, generally, it's like either I'm not getting it, or give this person more time, or comments like that. And I've had both in this particular presentation. So I wonder if I could just ask Doug. You said something to the effect of, "This is awesome." For those of the audience who maybe weren't quite getting it, what is your message? What's your take home from this?
Oh, at the risk of committing sacrilege in the minds of half of you, I will say that I am a quantum computing doubter, and view it a lot like the Emperor's new clothes. Although I'm happy, like with aliens, I'd be happy to be proven wrong. This, however, actually looks like it's a genuine dramatic leap forward that really does work. And I could see, in terms of what to do next, I could see things where instead of obsessing about finding the optimal solution, you could use this to program heuristics by giving intermediate rewards for partial solutions to the organisms and so on. So I see that partly this is awesome because a mole or 2 is a lot. Avogadro's number, 10 to the 23rd, is a really big number. We're used to dealing with millions and billions and trillions. You can divide by 10 to the 6 or 9 and 12, and what you have left is still a really big number. So I'm actually very excited about this as a dramatic new paradigm that goes in a way that we haven't really been exploiting so far.
So I got to ask, is Doug's interpretation accurate, or is he going off in another direction?
Go ahead.
He's very kind. So life has been doing this for a long time. So it's not that we can take credit for, we're basically using what's out there. Motion in life is computation, right? So when a protein moves from, the membrane of the cell to the interior of the cell or whatever, all of those can be thought of as process of computation. And as I said, on a very, very large scale, on massive scales. It's easy to think of the brain because we know we have like 1 billion neurons and they fire all the time. But every process of directed motion in any living organism is a process of computation. So life has been polishing this this set of tools for literally billions of years. So there's good reason to think that a lot of the engineering's been ironed out, basically, to put it that way. A lot of the work has been done on the hardware, on error control, the energy efficiency. I think this question wasn't quite answered as directly as we might have liked. The short answer is 5 orders of magnitude better than electronic computers. How much do we care about doing things 100,000 times more efficiently? I don't know. It depends how big the computer is. But a lot of this stuff has been ironed out.
Okay.
So that's good.
So I do want to give you some extra time, though, so we can answer a couple of these questions. Bo.
Yeah, so I'm going to ask this question. I understand I'm asking as a guy who once tried to build a computer with an ant colony. But the question I have is, when I'm looking at what you're doing, I believe in it, and I think you're on the right track. But why would I choose this option, which is a little more difficult to spin up, than something like agent-based modeling, using Repast or Swarm, or building a model like Sugarscape? Because it seems like you know the rules of the agents you're dealing with. So why not just virtualize them and avoid sort of the mess and trouble? Is it?
Do you want to take it?
I'll take this.
Okay.
So it's a very good question. If you try to virtualize it, you need a computer for that. And the computer that you'll be using, these things in front of you, work sequentially. They're very good at doing precise operations quickly, one at a time. But they essentially fail at things that require massively parallel computing. So the reason you would do this, for the same reason you do quantum computing or DNA computing, is that you do everything at the same time, and that's why you did the ant colony stuff. The advantage of something like this over something like a swarm or an ant colony is somewhat, perhaps paradoxically sounding, that in the cases of swarms or ants, they communicate. And that's bad. That's bad because what you want them to be is as dumb as possible, so that they explore every possible path. The ants leave pheromones and things, they run into each other, they communicate. And that helps them to do heuristics really well, right? But it makes them unable to find really weird minima globally far away from where they're looking. So they reinforce each other. So on some level, you want the agents to have like the minimum amount of intelligence. They need a little bit because otherwise they just fly off or whatever. But you want them to be as dumb as possible and no dumber.
I would just want to add that I would take issue, but not dumb, but non-intelligent. Okay, I will take issue with even parallel, even massively parallel. So what we propose is a combinatorial computation. It is not parallel. Parallel suggests that there are lanes, there are limited number of lanes. Okay, so it is a trademark, so we use massively parallel, but actually we're talking combinatorial computation.
Okay, and we'll take one more from Leo.
So I was wondering, so this is a reinforcement learning type of a system when you try all the examples and figure out how good they are. So it would be nice to see some examples, for example, a system that plays chess. Have you considered that?
We're very close to having something that solves Sudoku. So I don't know if you find that satisfactory. Chess is perhaps a little further away. I don't know if you have a thought on that.
Sorry.
I don't know if you have a thought on the chess thing. I mean, Sudoku is close enough to my mind that I'm like, it's okay.
Well, if you come to that, so if it is a test, we can feed I just suggested that the thieves could use our computer to steal the right selection of stuff. That would be an interesting application. And
all right.
Well, demonstration.
Dan, thank you very much. This was super interesting.
Thank you.